So before I go into today's notes, I want to just reiterate a couple of things that you should have watched yesterday from Pearson's example 4. When given the reciprocal function 1 over x, we realize that because you're never ever allowed to divide by 0, then the domain is going to be x cannot be 0. Remember that the domain is all the possible inputs, all the possible x values that you're allowed to plug in. And I'm allowed to divide any number, I'm allowed to divide 1 by anything, any number, except 0. So our domain became x cannot be 0. Our range became y cannot be 0. And then once we graphed it, we realized that there seems to be some sort of behavior where these 2 points that we graphed on each side seem to approach these lines. These lines were called an asymptote. It is a line that a graph approaches. And to approach a line, all it means is you get really close to it, but you never actually intersect it. With the horizontal asymptote, we were looking at the line, the horizontal line y equals 0, and then the vertical asymptote was going to be x equals 0. And what we're going to do is in this entire chapter is we're going to go ahead and shift 1 over x. This is the parent function of most of our functions in chapter 5. Alright, so now moving on. So this example that I'm about to go over, like example 1, actually comes from 4-1. So 4-2 I'm dividing into 2 days, but pretty much half of it comes from the first section of Pearson. And I'm going to post those examples on Google Classroom in case you want to look at them, and I highly encourage you to do so to make sure that you truly understand. So our essential question is, how do you graph a rational function of the form y equals a over x minus h plus k? So I'm going to show you one way, and then using Pearson you can see another way. So the first step is to always go ahead and find your vertical and your horizontal asymptote. Anything of the form that has a number over x is always going to have those asymptotes I just talked about, those lines that you approach but you never ever touch. So the very first step, step 1, is going to be to find the vertical and horizontal asymptotes. And then once you find them, you're going to go ahead and graph them. So for a vertical asymptote, you are saying what vertical line, for the vertical asymptote, it's very related to the actual asymptote. I'm going to go ahead and use my denominator, x minus h. So if I set x minus h equal to 0, I get x equals h. And that's going to be my vertical asymptote. For the horizontal asymptote, because we know that this fraction can never be 0 from before, the denominator cannot be 0. Therefore, a over a number can never itself be 0. So y is going to equal to 0 plus k. Or you can just remember it's pretty much the outside one. So the vertical asymptote comes from the denominator, and the horizontal asymptote comes from the y equals k. That's only if you have a number over x minus h. So remember, a is what we consider to be a constant. A constant is a number. Okay, so from that we know that the domain is pretty much x can be anything except h. For the range, y cannot equal to k. And I wish I would have switched these. For the vertical asymptote, it'll be x equals h, and for the horizontal asymptote, it's going to be y equals k. And remember, horizontal asymptote means a horizontal line. And horizontal lines come from y equals. Vertical asymptotes come from vertical lines. And vertical lines touch the x-axis, so it's got to be x equals. I wish I would have switched them. I'm sorry. Okay, so as soon as we find our asymptotes, we go ahead and graph them. So let's assume that this is h. So we're going to assume this is x equals h. And we're going to assume that k is way down here. Y equals k. I'm just making it up. Once you do that, your second step is going to be to make a t-chart. What's it called? Pearson actually uses shifts, and they make a t-chart on a over x. I'm going to show you a different way just because tomorrow's notes, we cannot use shifts, okay? Unless we rewrite it. But I'll try to show you both ways, but still. Okay, so we're going to make a t-chart. But for us, we're going to try to get used to tomorrow's method. We're going to center our t-chart, center it around the vertical asymptote. And then you're going to graph those points. So I'll show you what that looks like. But eventually, those 4 points that we graphed, 2 points before the vertical asymptote, 2 points after the vertical asymptote, we connect them, and then these arrows have to approach those asymptotes, okay? For the end behavior, it's kind of gnarly, so I'll go over it, but I don't think we're going to go over it again. So what's weird about this example is that now instead of having 2 end behaviors like we're used to, we have 4 end behaviors because there's 4 ends, there's 4 arrows. So we're used to doing something like as x goes to negative infinity and as x goes to positive infinity. And that would be talking about this arrow as x goes to negative infinity and that one as x goes to infinity. So as x goes to negative infinity, we notice that y is approaching this asymptote, which is the y value of k. And as x goes to positive infinity, I notice that this arrow is also approaching the asymptote, or y approaching k. The other one is weird, which we're going to do more of when we're most likely in pre-calc, unless I switch my mind. But it also comes in helpful in calculus. So in this case, we're going to look at this arrow. So for that one, we can see that x is approaching negative or positive h, or whatever that is. But this arrow is also approaching at h. The only difference is that one is coming from the right and the other one's coming from the left. So you'll notice that if I consider this one to be this arrow right here, I notice that this y value is going to infinity. And if I consider this arrow, I notice that this one's going to negative infinity. So how do I distinguish if they're both approaching h? So what we do later on is we say, well, as x goes to h from the positive side, so from the right side where things are positive, so we put a little plus, we see that the y goes to infinity. But if I approach the same x value from the left, or from the negative x values, then I see that this one's going to negative infinity. So again, I'm still debating. I don't think we'll do this again. But it comes in helpful for those of you who want to be like, you know, above and beyond. Alright, so let's get to it. That was a little confusing. Let's go to example 1. So on example 1 it says graph g of x equals 1 over x minus 3 plus 2. So this again is the same thing as example 5 on Pearson. So I'm going to show you one way and then you can see it Pearson's way. So first step is we're going to go ahead and find those asymptotes. My very first asymptote is going to be the vertical asymptote, which comes from my denominator. And then my horizontal asymptote, which as long as that's a number, it'll just be that. So vertical. Vertical means it comes from a vertical line, x equals. Horizontal means it comes from a horizontal line, y equals. Remember, horizontal lines touch the y, vertical lines touch the x. So if I set the denominator equal to 0, I see that the vertical asymptote is 3. And if I imagine that this approaches 0, then the leftover is y equals 2. So it's always going to be like denominator for vertical asymptote, where x comes from, and then you ignore that and it'll be y equals 2. So once I get those, I'm going to go ahead and graph them. So x equals 3, and we make a dotted line on x equals 3. And then we're going to go to y equals 2. We're going to make a dotted line, y equals 2. And then step 2, we're going to make a t-chart, and instead of just doing it on the parent function, which is what Pearson does, I'm going to show you how to use the original. So if I use the original, I'm looking to see what's happening before the asymptote and after the asymptote. So I'm going to put the asymptote of x equals 3 right in the middle. So if I plug in 3, I know that I'm going to get 1 over 0, so I know that this is going to be undefined. So I always put my vertical asymptote x equals in the middle. And once I put that in the middle, what I want to know is what happens before, what happens after. So I want to figure out what's happening at 2 and at 1. And then I want to figure out what's happening after, like at 4 and 5. From here, all I have to do is just plug it in. So 1 over 1 minus 3 plus 2. And that ends up being 1 over negative 2 plus 2, which is 1.5. You can take your time if you need to. If I plug in 2, I get 2 minus 3 plus 2, that's negative 1, plus 2 is 1. If I plug in 4, I get 4 minus 3 plus 2, which is, this is 1, because 4 minus 3 is 1, 1 over 1 is 1. 1 plus 2 is 3. And if I plug in 5, I end up getting 2.5. So I'll go ahead and I graph them. But because this is the original, I actually start graphing from the origin, because I haven't done any shady business by taking shortcuts or anything. So this is the original, so I graph from the origin. Original, origin. So from here, all I'm doing is I'm just going to go 1, 1.5, 2, 1, 4, 3, and 5, 2.5. And you can see that I'm never going to be like crossing in this case. So from here, I just connect them and just make sure that they approach the asymptotes. You are never allowed to actually touch the asymptote or cross it. So you want to make sure you graph your asymptotes and that you get close to them, but you're never going to cross them. You will get marked off if you do something like this. So if you have, these are your asymptotes, and then you do something like this, and something like this, you're going to get marked off, because then that means you're crossing the asymptote. If you do something weird, like this, and like this, you're going to get marked off, because this arrow needs to actually approach the asymptote. This arrow needs to approach this asymptote. So you want to make sure you watch out for that. Alright, so now we can go ahead and do the rest. So now my domain, remember, domain, denominator, domain, denominator. We look at the denominator. What can the denominator not equal to? Well, the denominator cannot equal to 3. It's very similar to the vertical asymptote, but the domain, remember, it's all the possible values that x can be. If you just put x equals 3, that means the only x value you're allowed to plug in is just 3. So what we're trying to say is x can be anything except that vertical asymptote. You can't touch it. You know? Can you touch this? Okay, sorry. So x cannot equal to 3. Domain, denominator. The range comes from your horizontal asymptote, but we're going to say y can be everything except 2. Horizontal asymptote, again, is y equals 2, because horizontal is a y. Vertical asymptote is an x value, x equals 3. The x-intercept is going to be somewhere right there. I see it, I just don't know what it is. So instead of finding the end behavior, let's do some math. To find the x-intercept, you're trying to make y equal to 0. So if I make y equal to 0, then we're going to get 0 equals 1 over x minus 3 plus 2. So I can subtract 2 from both sides. I can set this over 1 and cross multiply. So if I cross multiply those two, I get negative 2x plus 6 equals 1. And then after you solve, you subtract 6, you get negative 5, then you divide by negative 2, so you get 5 halves. Therefore, my x-intercept is going to be 5 halves, or 2.5 comma 0. For the y-intercept, I want to find y, which means we're going to get rid of x. We set x to 0, and if we do that, we get y equals 1 over 0 minus 3 plus 2. Oh shoot, I pointed to the wrong thing. I meant this is my x-intercept, and it looks like it would be 2.5. Which means this has to be my y-intercept, so I'm expecting like 1 point something. So if I do that, why did I put an equal sign? I'm all over the place, sorry. Then I get negative 1/3 plus 2, which is 1 2/3. So then I could say this is 0 comma 1 2/3, which it makes sense. So I double check, that looks like 1 2/3, that looks like it could be 2.5, so I'm good to go. Alright, example 2. Oh, sorry. So another way you can graph these is using Pearson's idea that you could just graph 1 over x, which is the parent function, and then just shift it to the right 3 up 2 units. Because remember, these are also shifts. Anytime you add anything next to x, it's going to move in the x direction. So 3 units to the right, and then 2 units up. So again, it is the same thing as taking this and moving all of these points 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, and then it would look something like this, you know? So that's how Pearson does it. But I'm going to try to not do that for this chapter, just because the next section, we're not allowed to do that, okay? And when you're moving sideways and up, it's hard to move whenever you have like little fractions of a number. But if you want to, go for it. You can also use transformations, and instead of making a table on the parent function, on the entire original function, you make it on the parent function, 1 over x. But like I said, I'm just going to show you this way. You already know the other way, kind of. Alright, example 2. Step 1. Vertical asymptote comes from x, so x equals the opposite, which is -4. Horizontal asymptote is going to be y equals -1. As long as that's a number, I could just take that value. So then I go ahead and sketch them. -4, -1. And so then again, this is x equals -4. This is y equals -1. Step 2, I'm going to make a table. You already know how to, if you were to do the other method, it would be the parent function would be -2 over x. But to avoid that, I'm just going to use the new method, which is just grab the original. It's how we used to graph in Algebra 1. And in order to figure out which numbers to plug in, I'm not going to plug in -2, -1, 0, 1, 2, because that's nowhere near the action, which is way over here. So I want to make sure I'm near the action. I want to see what's happening around here. So I'm going to make sure to put this x value of -4 in the middle, which I know is going to give me undefined. And then all I care about is 2 points before -4 and 2 points after. So that would be something like before -4 would be -5, -6, and after -4 would be like -3 and -2. So if I plug in -6, I can't fit. So I'm just going to do it on a sticky note. So -2 over -6 plus 4 minus 1, that's -2 over -2. So that's 1 minus 1, which is 0. And then -2 over -5 plus 4 minus 1. Remember, I'm plugging it into the original function. So that's -2 over -1. So that's 2 minus 1, which is 1. The next one is -3. So -2 over -3 plus 4 minus 1. And this happens to be -2 over 1 minus 1, which is -3. And then the last one, which will be plugging in -2. So remember, -2 plus 4 minus 1. Again, I'm using the original function. That's -2 over 2, which is -2. Because -1 minus 1 is -2. Okay, so then I can sketch. Because this is the original, I'm going to graph it from the origin. So I'm going to go to the left 6, 1, 2, 3, 4, 5, 6, 0. -5, 1. And this is going to be one of my arms. Approaching the asymptote, approaching the asymptote. I would know that I did it wrong if they happen to be like across an asymptote. For the other little arm, it'll be -3, -3, -2, -2. And then I'm going to approach the asymptotes. And you'll notice that they're the same distance away from your asymptote. And not only that, they happen to switch. Instead of having these two be the arms, they switched out because of the negative. Okay, our domain, remember, comes from our denominator. Domain, denominator. What can x not equal to? Well, x can be anything it wants except -4. Which is the same thing, it comes from your vertical asymptote. Vertical asymptote is the actual line, so you can get an equal sign. Domain is the restriction for x, which means x can be anything except -4. Range comes from my horizontal asymptote. We're saying y cannot equal to -1. It can be anything else except -1. And you can write it in interval notation. It would just have to be like from -infinity to -1 union -1 to infinity. You can also just look at the graph to figure that out. The x-intercept, I see that there's an x-intercept over here. It happened to be -6, 0. For the y-intercept, I see it over here. I'm expecting something like -1 point something. So to find it, if I don't know exactly what it is, we just set x equal to 0. And that'll be y equals -2 over 0 plus 4 minus 1. So that's -1/2 minus 1, which is -1.5. Which makes sense. So I can write it as -1.5 or -1.5. And so that's how we graph. Find the asymptotes, make a table, center it around the vertical asymptote, graph, make sure that those end behaviors are approaching the asymptote. And backside. Okay, so tomorrow's lesson is going to be, well, what if instead of graphing a number, like a constant, over x minus h plus k. Notice that all of these had numbers on top. Tomorrow's notes we're going to focus on, well, what if there's an x on top? Then I can't trust, I don't know who the horizontal asymptote is going to be. The vertical asymptote is still going to be the same, but what about that? So we're going to show you guys how to graph this again tomorrow, but you can also turn this into a rational function where there's a number on top plus a constant. We can do this using long division. So let's go ahead and do long division. Remember that we had in and out, in and out. So this is in, this is out. So in and out. And then from here we just said, okay, well, I'm looking at x and 4x. What do I multiply x by to make it into 4x? This is missing a 0, like a placeholder. So in order to make this into 4x, I need to multiply it by 4. And then I multiply both, so we get 4x minus 12. But then I subtract. So my remainder is 12. So technically, what we're saying is that g of x is equal to 4x minus over x minus 3. But I can also rewrite it as 4 plus 12 over x minus 3. So all I did is I took this and I literally divided it to see how many times it would go in. And I got that the quotient is 4 and that the remainder is 12 over the divisor. Therefore, g of x is equal to 12 over x minus 3 plus 4. And now it looks like everything else we've done in the front. I could tell that this is going to be a vertical asymptote. Because he's a number, my horizontal asymptote is going to be y equals 4. So we graph them, x equals 3, y equals 4. And if you're afraid to use a highlighter, you could just use a dotted line with your pencil. And then once we do that, I'm going to make a table on the original. And I can use 4x over x minus 3, or I can use the new original of 12 over x minus 3 plus 4. It doesn't matter. But again, in the middle, I need to put the vertical asymptote. I don't want to be right in the middle. I want to see where the action is at. I want to see what happens before 3 and after 3. So we put 3, which is going to give us undefined in the middle. Regardless of where you plug it in, it's going to be undefined. And then I plug in numbers before, numbers after. So if I plug 1, I get 4 over negative 2, which is negative 2. It's the same thing as if I plugged it in here. 12 over negative 2 plus 4, that's still negative 2. If I plug in 2, I get 8 over negative 1, so that's negative 8. And if I plug in, what am I plugging in? 2, I get 12 over negative 1 plus 4, which is still negative 8. If I plug in 4, I'm going to get 16 over 4 minus 3, which is 1, so that's 16. And it's the same thing as if I plugged it in here. 12 over 4 minus 3 is 1, plus 4 is 16. And if I plug in 5, I get 20 over 2, which is 10. And I would have had a different grid, because it's not going to fit. But we'll go with it. I think if I could do this again, I would have maybe done my table first, so that then I could scale them. If you use pencil, you can feel free to go back and scale it and go by 2s. It's up to you. Alright, so let's see if we can do this. Maybe it won't work. We'll see. 1, negative 2. 2, negative 8. 2, 4, 6, 8. Somewhere down there. And I'm just going to make sure that I approach my asymptotes. The next one is 3 undefined. 4 is 16. 2, 4, 6, 8, 10, 12, 14, 16. Way up there. Imagine it's way up there. And then we have 5, 10. 5, 2, 4, 6, 8, 10. Somewhere up there. And it's a similar distance. I just wish I wouldn't have ran out of paper. Okay, I hate myself. I don't hate myself. I just wish that I would have foreseen it, and then I would have just gone by 2s. But too late. Maybe if you still have a chance, you should do that. Okay, so domain, denominator, domain, denominator. The denominator is x minus 3. And we know that the denominator cannot equal to 0. Therefore, the domain is x cannot be 3. And I also can see it. X can be from negative infinity to 3, and then from 3 to infinity. So you can also write it in interval notation. Range y cannot equal to this y value of 4. Horizontal asymptote, vertical asymptote. Remember, horizontal means a horizontal line. Vertical means a vertical line. X-intercept, I see it somewhere there. So if I want to find it, I'm just going to set y equal to 0. And I could just do it into the original. So remember, x-intercept. I'm going to set y equal to 0. So that 0 equals 4x over x minus 3. If I put this over 1 and cross multiply, we get 0 equals 4x. So I know that x equals 0. Oh, so it was like right there, 0, 0. The y-intercept is going to be 0, 0 as well. And we're done. I'm sorry that took so long, and I'm sorry I messed up that example, but you'll be fine. Start your homework.